Examples for integration of bridges with roadways: 1. River bridges, bridges crossing river. 2. Viaduct, viaducts consists of a series of small spans to cross valley, river, roads, etc. 3. Flyovers are designed for fast-moving traffic to cross roads, railways, etc. Grade separators help to eliminate traffic conflicts by allowing one route to pass over or under another. Road over bridges allows road traffic to pass over obstacles such as railways, other roads, or rivers. An underpass is a structure that allows a road, railway, or pedestrian path to pass underneath another road, railway, or obstacle. An overpass is a bridge or elevated structure that allows one road or railway to pass over another. The integration of bridges with railways. Bridges are designed to carry the axle loads of the rolling stock, which move along the rails installed on the deck. Locomotives haul bulk and heavy commodities, and large number of passengers to a long distance. Now let us move on to the integration of bridge with waterway. Aqueducts must span a crossing at the same level as the watercourses on each end. A modern version of the aqueduct is a pipeline bridge. They may take the form of tunnels, networks of surface channels, and canals, covered clay pipes, or monumental bridges. Let's discuss about the integration of railway and waterway with a bridge. Pamban Bridge is a cantilever railway bridge of 2.65 km in length built across the Park Strait. It is India's first and second longest sea bridge, and third longest rail bridge in India. The Pamban Bridge, also known as the Rameswaram Bridge, is located in Rameswaram, Tamil Nadu, and connects Rameswaram Island to the mainland of India. It is a bascule bridge that allows ships to pass under the bridge. The two-lane Pamban Road Bridge runs parallel to the cantilever railway bridge. Let us discuss about the integration of roadway and railway with bridge. The Bogibeel Bridge is a rail-cum-road bridge over the Brahmaputra River in the Dibrugarh district of Assam state in northeast India. It is the longest rail-cum-road bridge in India with a total length of 4.94 kilometers. It enhances connectivity between Assam and Arunachal Pradesh and helps regional tourism, trade and commerce. Coming to bridge engineering, at first we will see what is bridge engineering. Bridge engineering is defined as a field of civil engineering that deals with the planning, design, construction, operation, and maintenance of bridges. Now, we will discuss each of one in detail. Let's discuss the planning of bridges and the steps involved in it. The planning sequence for the construction of a new highway or a railway project is a major part of project planning. Based on the complexity of the barrier across which the bridge must be constructed, the detailing of the project planning increases, because more investigation must be carried out. In general, the major steps that are involved in the planning for the construction of a new project are: identifying the need for the bridge, assessment of possible traffic in the area proposed to construct the bridge, study the location, study of all possible alternatives, refining and shortlisting all possible alternatives, identifying conceptual plans for the alternatives. This involves finding the materials, the arrangement of the span and the form, preliminary design and cost estimation, evaluating the alternatives, its risk, and the final choice of decision, resource source identification by detailed surveying, and implementation with the help of binding documents. This is followed by carrying out by fixing the agency, the construction details, and their commissioning. Next, let us discuss about the various classification of bridges. Generally, the bridges are classified based on the material for construction, structural form, and its usage. Let's see the various materials used for bridge construction. Bridges are constructed with various materials, like stone, timber, masonry, steel, concrete, steel composite, and pre-stressed concrete. Let's see the different structural forms of bridges. Based on the structural form, bridges are classified as slab, arch, beam and slab, truss, bowstring arch, cable strayed, suspension, extradast and balanced cantilever types. Bridges are classified into different types based on their usage. There are pedestrian bridges, road bridges, railway or metro bridges, road ******* rail bridges, and pipeline bridges. The other classifications of bridges are based on span, based on support type, based on alignment, and based on deck positioning. Types of erection methods. Pre-stressed I-girder using cranes. Balanced cantilever erected in segments. Cable-stayed, bridge carries mainly vertical loads acting on the girder. The structural form to be adopted is decided mainly based on the following aspects: functional requirement such as span arrangements, skew clearances, etc. There is an optimum or economic span range for every structural form within which it will be economical. We will elaborate on the same in the upcoming sessions. Structural requirement like the type of live loadings, which in turn depend on the intended usage, wind and earthquake, temperature impact, or collision loads, etc. The economic aspects refer to the importance of social responsibility, constructional limitations like shuttering, erection launching, construction time, etc. The specific structural form is adopted for specific construction methodology, durability requirements, such as service life. Site specifics and exposure conditions, including geotechnical and topographical features, operation aspects, such as mobility, and maintenance aspects, such as frequency and nature of periodic maintenance, etc. Aesthetic considerations are also very important, as bridges are usually long-lasting landmarks that define the architectural signature of a period. Future considerations includes widening the carriageway in the future. Not every structural form could be widened in the case of anticipated future widening. Slab bridges and beam and slab bridges are the most common structural forms. Adopted bridges may be classified on various bases. Slab bridges and beam and slab bridges are the most common structural forms. Adopted bridges may be classified on various bases. In this section, we intend to list out the classifications according to the adopted structural form or structural system. In turn, this depends on the span and the load-carrying capacity of the bridge. The major structural forms used in today's industry are slab, arch, beam and slab, box girder, truss, bowstring arch, cable-stayed, suspension, balanced cantilever. Various structural system will be discussed in detail in the following sessions. Let's look at slab, or voided slab type. This is the simplest structural form for a bridge superstructure, and has been used since ancient times. In comparison to beam and slab structural forms, concrete and steel material consumption is higher. However, construction costs, such as formwork and labor, are lower, so the overall economy will vary. Overall economy, when compared to other structural forms, also depend on the loading type, clearance below bridge skew or curvature, etc. The main flexural member shall be RCC solid slab for spans less than 8 m, RCC voided slab for spans between 8 to 15 m, and pre-stressed voided slab for spans between 15 to 30 m.
Arches are attractive as well as one of the earliest and crudest methods of pre-stressing in bridge construction. Even today, spans up to 550 meters are constructed using this structural form. Let's look at the beam and slab type structural form. The most commonly adopted structural form in today's bridge engineering industry is the beam and slab form. This system consists of longitudinal beams or girders that span between the supports and support the transversely spanning deck slab. Girders are typically designed as I or T beams, with a deck contributing significantly to compression through composite action. Girders can be cast in situ or precast, which makes them composite with a deck slab via interfacial shear links. A reinforced cement concrete or RCC girder is used for spans up to 25 meters, and a pre-stressed concrete or PSA girder is used for spans between 25 and 40 meters. Support types shall be simply supported, continuous and integral, whereby simply supported is most common. Transverse beams or diaphragms are usually provided at intermediate locations or supports to provide lateral stability and to distribute loads between the girders. Box girder type superstructure. This structural form is an improvement of the beam and slab system, which has been evolved to cater the specific needs like constructional requirements or structural requirements, support types or alignment features. In case of pre-stressed concrete girders, box cross-sections offer an economic edge over the conventional I-girder because all pre-stressing cables can be kept at maximum eccentricity, which is in the bottom flange. Whereas in I-girders few of them might need to be placed in the web also. If the eccentricity is greater, there is an increase in load carrying capacity. It is the most suitable cross-section for curved alignments due to the high torsional rigidity of closed sections when compared to open sections like I-girders. It is usually used for spans between 30 and 50 meters. The superstructure can be made of pre-stressed concrete, which is the most common, or of reinforced concrete. In addition, box-type structural forms are more suitable for balanced cantilever construction than conventional girders. It is also ideal for integral or continuous spans where hogging moments may arise as the section has higher moment of inertia for both hogging and sagging moments. Compared to the conventional I-girders with composite deck slabs, which have a higher moment of inertia for sagging moments than the hogging moment. During the earlier periods, truss-type structures were preferred for long span bridges. Spans of up to 550 meters were constructed for the Canada-Quebec Bridge in 1917. Although the truss-type superstructures are usually made of steel, timber was initially used and concrete was added over time. Truss bridges with a span of up to 500 meters were constructed. It is easier and faster to construct due to lighter members and the ability to assemble on-site as compared to other forms. Therefore, it is the usually preferred structural form for rail over bridges for spans greater than 50 meters over rail tracks in use. Deck type or through type forms are being used. We will discuss these types in the upcoming sessions. Coming to bowstring type structural form, it is a modified version of arch bridges. In this type, a pair of arches is usually provided on either side of the deck. Typically, these archways are braced together to provide lateral stability. A bowstring arch is typically made of steel, concrete or steel composite material. Under the deck, the load is transferred to cross girders, which then transfer the load to the longitudinal girders and subsequently to the arch through hanger. Horizontal thrust at supports is boned by the longitudinal tie. This type of structural form is usually adopted for spans from 40 to 80 meters and at locations where higher navigational clearance is required below the deck. Now, let's take a look at the cable stayed type structural form. This is the most commonly used structural form for long span bridges today. For long spans, design forces are reduced by providing intermediate support stays at intervals, which transfers the loads to the pylon, which is the tower-like structure of the substructure that supports all cables and in turn transfers the loads through the foundation. It is possible to use centrally supported systems or edge-supported systems. For centrally supported deck systems, one set of stays may be attached to the central median portion. In contrast, for edge-supported deck systems, two sets of stays may be attached to the outer edges. The inclined stays also provide pre-stressing to the deck, which enhances the load-carrying capacity of the deck. Cross-sections of decks are typically box-shaped or strutted, box-shaped or spine and wing-shaped, etc. for centrally supported systems or I-girders or twin-box girders for its supported systems. Extradose bridges combine the concepts of pre-stressed box girder bridge and a cable stayed bridge with lesser eccentricity for the cables. The pylons are shorter than a cable stayed bridge, the girders are shallow compared to a girder bridge, they are commonly used for spans greater than 50 meters. Coming to suspension-type structural form, the suspension bridge has been built since the early 1800s. Long-span bridges usually use suspension bridges. The suspension type of structure form is being used to build bridges with nearly 2-kilometer spans. A deck or longitudinal member can be suspended at intermediate locations by suspender cables called hangers. These suspension cables in turn can be suspended by suspension cables suspended between towers. Suspension cables are anchored at either end to the ground or to anchor blocks. A pair of suspension cables are usually installed at either end of the deck to ensure stability. Longitudinal members are constructed with steel and concrete. Let's take a look at balance cantilevers type structural form. The structural form is developed from the balance cantilever construction method to reduce longitudinal bending during construction. Based on their usage, bridges are classified as pedestrian, road, rail bridge, road-cum-rail, and pipelines. Let's take a look at pedestrian bridges. The purpose of these bridges is to carry pedestrians or cyclists over an obstruction. These bridges are subjected to lesser loading and requires lesser carriageway width when compared to other types. They are usually designed to bear a load of 5 kN per square meter, or 500 kg per square meter. Most pedestrian bridges are made of steel due to aesthetic and constructability aspects. Now, coming to road bridges are the most common types of bridges. It is further subdivided according to the nature of obstruction or crossing. A flyover is a bridge over another road that allows traffic to flow uninterruptedly with approaches from both sides. Grade separator bridge facilitates movement of traffic by segregating at grade, conflicting movements to different levels. Road over bridge, or ROB, built over the railway tracks. Underpasses structure allowing uninterrupted movement of traffic beneath a reference roadway. Overpass bridge carrying another road over a reference road. Let us now look at bridges for rail-based transit systems. Bridges of this type are designed to convey rail-based transit systems across obstructions. Today, they are very relevant and common since most of them are built and operated on viaducts over existing roads due to the lack of land availability. Such bridges are designed to carry the axle loads of rolling stock, which move along rails installed on the deck. Hence, they do not need to be checked for lateral movement of live load. In the case of road bridges where the vehicle can move longitudinally and transversely, this is an extremely significant difference between the road and the rail bridge. Rail structure interaction, also known as RSI, plays an important role in the design, especially if the spans are more than 50 meters. Nosing force and derailment loads are also unique to rail-based transit systems. Coming to road-cum-rail bridges, they generally adopt the form of double-decker, one deck above the other. Two separate transit systems are needed, one for road traffic and another for rail-based transit. It provides space savings and reduces construction costs. Substructure and foundation must be designed for both rail and road loading. Bridge designs are usually performed based on the design guidelines or codes for both rail and road bridges, and the critical forces of each are adopted for design. Let's look into pipeline bridges and aqueducts. Bridges are not designed or constructed just to carry people or traffic over obstructions. They may also carry water, oil, etc. Pipeline bridges carry oil or gas pipelines and are usually made of steel. These bridges typically adopt a truss, cable-stayed, or suspension-type structural forms. Pipeline bridges of spans up to 720 meters are constructed. Nowadays, provisions are made to support pipelines on the S. Pipeline bridges. Pipple line bridges carry oil or gas pipelines. They are usually made of steel. And of spans up to 720 m are constructed. Aqueducts. Aqueducts carry canals and are often constructed as RCC. Navigable aqueducts that permit boats or vessels are also being constructed. Normally up to 125 m are constructed. Types of bridge based on spans. Culverts are of span less than 6 m. Minor bridges are of span between 6-60 m. Major bridge are of span greater than 60 m. Long bridges are of span greater than 150 m. Classification based on support types are simply supported, continuous, integral, balanced cantilever, cable supported. Now let's take a look at continuous support. Bridge superstructures are continuous over multiple spans, longitudinally over bearing supports. Compared to simply supported designs, gravity loads generate hogging movements at supports, reducing sagging moments at mid-span, which may lead to economic design. This system is more complex in terms of design and construction when compared to simply supported. A continuous bridge is a statistically indeterminate structure since it has more than two supports. Creep, shrinkage, differential temperature, hyperstatic or secondary effects of prestress, etc. should have taken into account during design. The construction scheme should also be considered as the structural system may change over time. Integral bridges have longitudinally flexible substructures like tall piers, portal piers, wall piers, etc. to minimize the negative effects of longitudinal deformations like temperature, shrinkage, creep, etc. Bearings and expansion joints are not required, so maintenance efforts are lesser. This system is especially suited for curved alignments where uplift is anticipated, since provision of bearings at those locations will be challenging. Coming to the balanced cantilever systems, it is an evolved integral support system modified to accommodate the requirements of balanced cantilever construction. The cross-sections it supports is larger due to the fact that they need to support long cantilever lengths of superstructure during construction time, so they tend to attract more bending moments. The mid-span sections may be smaller since the design bending moment and shear force are lesser. The superstructure is mostly made of pre-stressed concrete, though RCC is also rarely used. Bearings may be used in the case of continuous bridge or may not be used as it is in the case of integral bridge. Rigid frame partially articulated with hinges or articulated with suspended span arrangements may be adopted even though rigid frame type is the most commonly adopted system. Finally, we have cable-supported or suspension or extradosed. They are commonly used when the span is more generally greater than 50 meters. With a longer span, bending moments and shear forces increase significantly if intermediate supports are not provided for the superstructure. As a result, the superstructure must be supported at intermediate locations. This is usually done with cable stays or hangers which support the deck at intermediate locations in addition to supports at pier or abutment locations. Bearings are typically provided at abutment locations, construction stages, and deformation-induced loadings must be considered as the structure is statically indeterminate. Let's summarize all that you have learned. In simply supported span is supported at both ends by bearings placed on top of the pier cap. In continuous type, bridge superstructure are continuous over multiple spans, longitudinally over bearing supports. The superstructure is monolithic with the substructure of integral type. Balanced cantilever is an evolved integral support system modified to accommodate the requirements of balanced cantilever construction. Cable-supported or suspension or extradosed systems are commonly used when the span is more generally greater than 50 meters.